Some time ago, I demonstrated the catastrophic failure of a macrame hitch.
Jesus! Oh!
Since then, I've been curious as to the safety of releasable systems, and since I couldn't find a lot of information on this topic, I have decided to do my own research. For my tests, I have decided to measure the pull-down force of a system after it has been weighted with a 2-person rescue load, the pull-down force of a system with an abseiler on rope, the force required to pull down a system while rappelling, and whether a system can hold the force of a person falling onto it. For this test, I'm dropping an 80 kilo weight onto 600 millimeters directly onto the system. .27 kilonewtons. .23 kilonewtons. .25. 0.7. Oh. Seems to work just fine to me. When I first started these tests, I didn't have a toggle stick, so I improvised using a tent peg, which didn't perform very well. I then found a steel pipe, which performed a lot better. However, the weight of a steel pipe falling on an abseiler could be dangerous. I then used a piece of PVC pipe. However, the PVC can be deformed under load, which can make it difficult or impossible to remove. I then bought a piece of HDPE and manufactured my own toggle, which performs very well. .46. .46 kilonewtons. Right, 1.32 kilonewtons. 1.69 kilonewtons. 1.31 kilonewtons. Again. 1.76. Three kilonewtons. That's 4 kilonewtons. 3.99. It's not coming out. .8. So that's 1.5. I know the ball for that. 1.5. 1.58. 1.62. That's done something. 0.72. 0.89. That's me. 0.9. That's me. That's hot. That is a sheet bend. Off rope. Seems good enough. The stone knot is tied to the stick. However, instead of using a stick, you pass a bunch of bites of rope through the knot to form your block. From what I have read, you should use 5 bites of rope. I haven't tested it with less, however, it would definitely depend on the type of rope you are using. In my test, it worked very well, and on the loaded and snagged pull-down tests, it became impossible to remove. So far we're at 0.31. .31 kilonewtons. Here, I'll stop pulling. So to pull a bite out of the hull took 0.77 kilonewtons. To pull the pull rope out took 2.11 kilonewtons. Now we are lifting the abseiler at 2.1. .11 kilonewtons. We are pulling the CEM out. This one actually requires quite a bit. Give me some more. Back up. So I'm actually lifting. Ooh, there we go. 0.72 kilonewtons. Seems to work. .19. Where are we at? 2.4. There we go. something. Right, 2.88 kilonewtons. Slipping down the tree. 2.93. Yep, that's it. So 3.93. Go down, see. So you can improve on it. No. Don't know. That's 3 kilonewtons. 3 kilonewtons not coming out. 0.59. 0.78. Seems to work. I tested two variants of the CEM knot. While they both work just fine and they seem safe enough, I'm just not a huge fan of the way that they pull out. And we shall release the macrame. .36 kilonewtons. So that's pulling at 0.6 kilonewtons. 0.9. 0.96 kilonewtons. So I'll just start rappelling here. The snag is catching and it will pull out at 0.80 kilonewtons. Seems to work. Alright, so we just done the one drop test on macrame. What happens if we put the load on the backup rope, on the pull side of the rope, and then drop onto it? And that's as high as we go. Ooh, that's not so good. It's held. But it's taking out a lot of that knot. I like the macrame knot because the pull down is very reliable, and if an abseiler jumps on the wrong strand, it has some redundancy built into it. However, if you load both strands at the same time, it will fail catastrophically. Right. Wait. 0.23 kilonewtons. .22 kilonewtons. Here we go. We got the first bite out. Oh, and it's gone. That took 4.22 kilonewtons. So we're at 0.8 kilonewtons. Woo! 0.87 kilonewtons. Didn't see that becoming a problem. The releasable bowline has a very low pull down force and a high loaded pull down force. However, on a large rappel, the pull down force may be higher due to the weight of the rope. Also, the releasable bowline can jiggle loose while unweighted. .38 kilonewtons. Okay, so that's pulled the bite out from underneath the hitch at 1.91 kilonewtons. Now to release the rest of the hitch is extremely easy. Why is that caught? That is caught on something. .91. .66 kilonewtons. Oh, starting to take up on the good. 0.66 kilonewtons. 0.80 kilonewtons. 0.80 kilonewtons. The JRB hitch cinches down tight against the anchor, which can prevent the knot from sliding on the anchor material. However, the high loaded pull down force is due to the locking bite being trapped underneath the weight of the abseiler. When I tested the knot while the locking bite was loose, it came out very easily. Here is the results of my testing. My testing was done in a sterile environment and I only used one rope in my tests. Different situations may produce different results. These systems are inherently dangerous. Test your own systems in a safe manner before use.